Hey guys, Unit 7, lesson number 8 today, talking about why it's not always ideal. Alright, I'm going to do my best to keep my eyes here, but my work here, and we got lots of stuff we're going to be working with, so if you need to hit pause to gather any materials or make something, follow along with me. Lesson 8 is talking about when things get strange, right, when it's not ideal. We've been talking about what the probability is of something happening, but what happens if that probability doesn't turn out exactly like we were expecting, right? That's the whole point of this, is that statistics, we do studies because there are variations in everything that we're studying and what we're looking at. Statistics will tell you which football team, for example, should win on a Sunday for the NFL. You can run statistics and people make their choices, they place bets, they make decisions about who they think is going to win and by how much. But the players still have to play the game because, honestly, something strange can happen. So that's why they still play. So we're thinking about in 8.1, how closely data matches what we would expect to happen. Lynn, Kieran, and Diego are going to shoot 100 free throws each for practice. Based on their shooting in the past, Lynn thinks they are all of similar ability. And Lynn estimates that they each have a 60% chance of making each shot. So then they shoot 100 times. Okay, so they're doing free throws for basketball. Lynn makes 63 out of 100 shots. Kieran makes 75 of the 100 shots. Diego makes 35 of the 100 shots. So we can find those percentages pretty quickly because they're each out of 100. 63%, 75%, and 35%. So from our results, we want to see if we agree with Lynn's estimate for the chance that each person making each shot. Explain your reasoning. We could argue both ways on this, right? Lynn, before they took their 100 shots, Lynn thought about what they did in the past and said they each had a 60% chance of making each shot, right? And so then they looked at how many out of their 100. Lynn was spot on about their own shots, maybe underestimated Kieran, and maybe overestimated Diego, because Diego only has 35, pretty far short of 60. So I would agree with Lynn's estimate for Lynn and for Kieran, but not so much for Diego. But we also have to know that there is some variation. Diego might just be having a bad day. Maybe Diego pulled a muscle or is still thinking about that science test that he took beforehand. And so there might be a reason why Diego's just having an off day. So we could have some ideas about why, yes, we would agree with Lynn. Maybe there is some historical data. Maybe Lynn was thinking about the average of all three, because the average of all three of them is about 60%. Or maybe Lynn and Kieran are just having a good day and Diego's just having a bad day. So maybe Diego's just having a bad day. I'm going to call it an off day. So that's a possibility. We might disagree with Lynn. We might say, no, Lynn is not right with this estimate. Lynn is overestimating some things or underestimating others, or is oversimplifying just how hard it is to keep a consistent shot in basketball. Sorry, I got distracted for a second there. So we could say that Lynn is not right. Lynn maybe overestimated Diego can't see that because of my camera there. So maybe overestimated Diego just because Diego's pretty far off of that 60%. And Diego's actual performance was much lower. So, you know, we could argue either way, this idea. So this is what we're talking about, that it's not always ideal. Somewhere in there has to be a line about what is within that normal range and what's outside that normal range. We'll be talking about that in a couple lessons to come. So we're going to keep thinking about what's normal and average, what we expect versus what we actually find and see. When we go to 18.8.2, what is reasonable? So here we're talking about the probability of flipping heads using the coin you have. So maybe you want to go find a coin. I'm going to use this one here. I've got a penny. It's a standard penny, Lincoln on one side, the Lincoln Memorial on the other. And the probability that you flip heads, well, there are two possibilities. Only one of them is heads. So we have a 1 in 2 probability of that happening. We can display it as a fraction, or we could put it as a percentage, a 50% probability, or even as a decimal, a 0.5% chance. Any way that we want to express it, we could say that. So if we were to estimate the number of heads we would get if we flipped a coin 20 times, we would expect half the time that it would come up heads. So 1/2 of 20 times is 10 times. Now that's what we would expect. But we don't live in a perfect world. We're going to flip this coin 20 times and record the number of heads we get. And then we're going to do that 5 times. So each of these trials that we have is 20 flips that we're doing, each one. So in order to do this a little bit faster, because I could sit here and flip a coin and flip a coin and flip a coin, and it could look all funny here because I'm trying to do it under a camera and in the space that we see. Instead of that, I got 20 coins. One's a dime. And I'm just going to shake them and then spill them out here on my table. And we're going to count how many of them are heads and how many of them are tails. Now, if you're just doing this with 1 coin or 2 coins, you could do the same kind of thing. You could flip them or spin them or shake them or however you want to do it. But this is a way to kind of speed this part up so I can do all these 5 trials at once, because then we're going to see a bunch of other data. We're supposed to collect it from the whole class. So mixing, 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 dropping, and now I'm going to count the number of heads I have. All right, so I'm not going to flip any of them over. 1 head, 2, 3, 4, 5, 6, 7, 8, 9 heads. So there's my first trial. So you get the sense of kind of how we're doing this here. Now, the reason why we're flipping coins and caring about this stuff is that we can start to use these as simulations later. Sometimes we don't always want to run an experiment, and if there's something that's got a chance of one or another, we could flip a coin to simulate it. This could be something like whether whether a baby is born as a boy or a girl, kind of thing, 50-50. So I just did it again. 1, 2, 3, 4, 5, 6, 7, 8, 9 heads again. Here we go again. Shake, shake, shake. Mix, flip. That one came out ahead, so I'm just going to leave it that way. And let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 this time. I dropped one and it was spinning on my desk. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's funny, I was expecting to get 10 and I haven't gotten a 10 yet. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9 heads. So this is my information that I got here. Not a single time did I flip 10 exact heads. But I can record that data and start to get a pattern of what's happening. In 8.3, question number 8.2, sorry, question number 4, it asks us to create a dot plot that shows the number of heads in 20 flips using data from the whole class. So if we had everybody, we could make this dot plot going on. Now obviously the lowest number of heads we could get is 0 and the highest was 20. We're expecting a lot of 10s, I would guess. In between here is going to be 5, so 1, 2, 3, 4, 6, 7, 8, 9. Here is going to be a 15, 11, 12, 13, 14, 16, 17, 18, 19. I'm just going to mark a couple of these key ones because I think I'm going to use them a lot. So our results that we need to log first for what we just saw was 9, 12, 11, and 9. So 9, 9, 12, 11, and 9. Now we're supposed to gather this information for the whole class. I don't have a whole class of data to pull right now, so I'm going to hit pause on my video and I'm going to do this like 10 more times. Alright, so I'm just going to keep on putting some more. I want to get about 20 dots on here, so I'm going to go ahead and hit pause. When I come back, you'll see my results. I actually did this. Alright, so I'm back. So I kept on flipping all of my coins and I kept on doing it again and again, and these are the results that I found. Maybe you want to add this to yours. I got one time where I got 5, one at 7, 8 heads happened 3 times, 9 heads happened 1, 2, 3, 4, 5, 6, 7 times. So I put some numbers up above here. 1, 3, 7. This is 6 for 10. 11 happened 4 times, 12 happened 5, 13 happened twice, and 15 happened once. So this is the results that I did when I did it 30 times. Now remember, each of these 30 trials represents 20 coins, so man, we're talking about a lot of data that we just gathered here. The fewest number of heads flipped by our class in 20 flips, in our case, was 5. The greatest was 15. Based on our class dot plot describing a range of values that represent a reasonable number of heads, well, it's reasonable that we got 5 to 15, but when we think of reasonable, we kind of want to get that as narrowed. These are kind of some oddballs. They only happened once. So I might say a good reasonable number was 8 to 13. Okay, so it's completely normal to find about 8 to 13 heads every time we flip 20 coins. So Priya flips her coin 20 times and it lands showing heads twice. So 2 out of 20. Is it possible for this to happen with a fair coin? Absolutely, it's possible. It's not common, but it is possible. Now, if she did this a whole bunch of times and she kept getting 2 heads or 3 heads or 1 head on these 20 flips, then I would start to get suspicious, right? But just her getting it one time, that's not completely unheard of, all right? So reasonable, right, is what we would expect. Possible is everything from 0 to 20. Based on our class distribution, should she be suspicious of this being an unfair coin? What can she do to provide evidence that it's not a fair coin? Should she be suspicious? I would say that if it's one trial, has 2 of 20, I don't know that I'd be suspicious. Not suspicious. And to prove evidence that it's is or isn't a fair coin, I would say, if we're looking for evidence, do more trials. If she did a bunch of trials like I just did with all of my coins right here, she could do a bunch of trials like that, and she would be able to tell if it's a fair coin or if there's something tricky or wrong with it. So there is definitely just repetition. Repetition, repetition. Everything that they do, they repeat. Every test they do in the medical field, they repeat it. A doctor has to be able to do it in another lab. A scientist who's studying biology, if they see it in one lake or river or stream, they're going to go check it out in another river or stream and see if they're seeing the same thing. So this is very common for us to do. If we think something is suspicious, we're going to repeat it. And if we get the same results again and again in different locations, then we're going to trust that it has to be true. Now you can check out the Are You Ready for More, right? We're talking about how many times it takes to get a heads. Kind of a neat way to think about it. And so you could think about that as far as taking a single coin and counting how many flips it takes to get that heads. We would imagine it would take only 1 or 2 flips to get a head, but sometimes you might have a single coin go on a streak where you get tails a bunch of times, so kind of a neat Are You Ready for More to think about what that might be. 8.3 talks about something being fair or not. We love to call things fair or unfair. Let's read our whole situation going on here, all right? The local news station wants to interview 8 students from a school. There are 25 students on the student council. 10 of the students are from the graduating class, seniors, and 15 are from other classes, freshmen, sophomores, and juniors. The principal has a difficult time deciding which students from the council will get interviewed for this local news station. So she tells the group of students that she will put all of the names in a bowl, mix the names up, and then the first 8 names who are selected from the bowl will get to be interviewed. The next day, the principal returns with the names selected. It turns out that 5 of the students who get to be interviewed are in the graduating class, and only 3 of the students selected are from other classes. Students who are not in the graduating class complain that it doesn't seem fair. They suspect the principal chose the group rather than selecting at random. Let's think. Do you think the principal could have chosen this group of students at random like she promised? Explain your reasoning. Well, it is possible that from, what do we have total? 25 students? From that batch of 25 students, she could have picked 0 from the graduating class, or all 8 could have been grads. So when we think about what is possible, she could have picked 8 names, and 8 of them could have all been from the graduating class. There are 10 of them from the graduating class. It is possible that she could have picked 8 of those 10 out of all 25 names. Now, it's highly unlikely, all right? It's just like flipping a coin and having only one head out of 20, right? So it is possible. In fact, I think that it's very probable. It is more likely that of these 8 names, if there are a little more than half of the students, let's see, 10 out of 25. So if we think about 10 of them are seniors, and then 15 are from all of the other grades, freshmen, sophomores, and juniors, that might mean 5 from each of those other classes. So there's twice as many seniors as there are any other grade. Now, while all these other grades make up more of the student council of the 25, they make a majority of those 25 students in total, we would expect more than half of those 8 names. We would expect 5 of those names to have been underclassmen, whereas this one, 5 of those names was graduates. Now, that's not that big of a difference, though. It's not like one person was an underclassman and 7 of them were over. So I would say it is even probable that 5 of the 8 names are grads. This seems okay. It is much more likely it is most likely that 5 of 8 would be non-grads. This is what's most likely, but this isn't that far off to get 5 out of 8 that are graduates. We are going to do a simulation. This one asks us to cut a piece of paper into 20 equal sized pieces. Now, what's funny, we could have done this with pieces of paper like they're about to say. We wouldn't do this with a coin flip. Okay, we can't simulate this situation with a coin flip because it's not an even 50-50. It's not that there's 10 seniors and 10 non-seniors. It's not 50-50. So that's why we're not going to do like flipping coins of this. Instead, they ask us to cut 25 pieces of paper, and on 10 of them, write graduating class, and on 15, write other classes. Now, I have already got this set up, so if you're going to do this for yourself, you might need to, but I've already got them all cut out. So I've got 10 of these little pieces of paper that say grad, and 15 that say other. Okay, I just dropped one, so I need to pick it up. All right. Gotta be fair, right? It's just like this principle, I have to be fair. Mix them up, take turns with our partner, draw 8 pieces of paper, and record the students chosen in the graduating class. Repeat it 4 times. So we're going to do this again like we did with the flipping coins. And we're going to record our numbers and our data here in this chart. And then it says, again, to create a dot plot of everybody in our class, and then look at our dot plot and make some conclusions. All right. So hold tight, I'm going to get a cup. All right, I got my handy dandy Yahtzee cup. There it is. There it is. So I got my Yahtzee cup. I'm putting all my pieces of paper into my Yahtzee cup. There they all are. Shake, shake, shake. Blindly pick. I'm not looking, although you get the results because you can see. I have a grad, a non, 2, 3, 4, 5, 6, 7, 8. That one was the hardest because I had to make sure I only had one. All right. And of the 8 I picked, 1, 2, 3, 4, 5, 6, 7, 8. I picked one too many. That was the last one I picked. Whew. Talk about changing the results. 1, 2, 3, 4, 5 grads and 3 others. I got the same exact result as the principal did. 5 grads. All right, I'm going to put it in, mix it up. Kind of want a bigger cup. There we go. Now I can mix it up. All right, pick an 8 again. 2, 3, 4, 5, 6, 7, 8. 1 grad, 2 grads, 3, 4, 5 grads. I got the same thing. Trial number 3. 1, 2, 3, 4, 5, 6, 7, 8. Other. 1 grad, 2 grads, 3 grads. All right. Exactly flipped the results. That's interesting. Math is so exciting. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. Three grads again, and one more trial to go. One, 2, 3, 4, 5, 6, 7, 8. And this one is exactly 50-50. So we've got 4 grads, 4 others, and poof, now we've got our answer. All right, so we know the lowest number of grads we could pick, the highest number is, was 0, the highest number is 8. Somewhere in the middle is going to be 4, 5, 6, 7. 1, 2, 3. All of these are possibilities. The ones that we just showed you are a 5, a 5, a 3, a 3, and a 4. Through the magic of video, I'm going to try to replicate an entire class of responses. I'll be back in a long time. That took me a long time. These are my results. I got one time where I got 1 graduate, 2, 3, 4, 5 times that I got 2. 2, 3, 4, 5, 6, 7, 8, 9 times that I got 3. 3, 4, 5, 6, 7 times that I got 4. 6 times I got 5, and 1 that I got 6, and I even got one where I got 7 graduates. So this is what my dot plot looked like when I replicated this a bunch more times. Based on our dot plot, do you think it is reasonable that the principal selected the students for the interview at random and still chose 5 out of 8 students who were in the graduating class? I'm going to say yes. It is reasonable. In our case, it happened. So I'm going to say in my trials, it happened 6 of 30 times. I think I did it 30 times. 10, 20, yeah, 30. 6 out of 30 times. So that's not unheard of, right? It happened more than once. It happened pretty commonly, nearly a fifth of the time. So that's not such a big deal for it. So it happened 6 of 30 times, while 3 was the most. The most frequent number five, 6, and 7 also showed up. So I don't think this principal was trying to fool anybody. Maybe if they're really going to accuse her of that, they should, she should have done it in front of them. But still, it makes sense. So our lesson summary, making sure that's the end. Yep. The lesson summary just kind of walks you through some of these ideas. We model situations because predictions are one thing, but actual results often don't match predictions exactly. That's our idea. So a single result that is different shouldn't make us say, well, that can't be right, let's throw it out. We want to then instead repeat it. So repetition is a great way to add validity to a test. So, it goes through the coin flipping thing. We want to always think about what is normal, what we expect, but we always expect a little bit of wiggle room, a little high, a little low, what our exact prediction is. So a good mathematician will use data to suggest a model that can approximate a situation, then reevaluate that model, testing it against additional data. So that's our big idea. We want to revise and revisit. We want to make it better and better. So repetition is good. Repeat. And I'm going to just call it wiggle room. That wiggle room around our norm. The wiggle room around our expectation is normal. Okay, and that expectation is what we usually think of as the average, the mean, the norm, the middle. Okay, so wiggle room around that is okay. That's our lesson 8. Go tackle those practice problems. We'll see you guys later.